How can we enable agents to continuously and autonomously learn useful skills? For example, if we took a robot, attached a camera to it, and left it alone, could it autonomously learn to move its hand and to manipulate objects in front of it, like this door? Let's consider what it would take to develop such a system. First, we need to define an objective that quantifies these desires so that we can measure progress and develop principled methods towards this end. Next, we need to be able to optimize this objective in a way that scales to high-dimensional state spaces, like those in vision-based tasks. Lastly, if we want to apply this in the real world, we need to make sure that the method doesn't require extensive engineering, meaning that we want to avoid manually designed reward functions or additional sensors for each new environment. In this video, I'll present an objective for autonomous learning, a method for attractively optimizing it, as well as simulated and real-world robot results demonstrating our method's capabilities. Let's first talk about the objective function. For autonomous learning without rewards, a common approach is to perform exploration, which typically optimizes some measure of state visitation frequency or prediction error. We can formalize the exploration objective as wanting to maximize the entropy of the policy's marginal state distribution. This objective says that if a robot starts in the bottom left corner of the environment, it should explore and cover the entire state space, rather than stay in the corner. However, we also want to be able to control this robot. So we add this second term, which says that we should be able to control the robot by setting goals, which are just states that we want the robot to reach. Unfortunately, this objective can be difficult to optimize, as it requires computing and optimizing the marginal state distribution entropy, which depends both on the policy and the potentially unknown environment dynamics. We can avoid this challenging optimization by noting that this objective is simply the mutual information between the goals and the states, which we can rewrite as follows. The second term is the conditional entropy of the goal, given the state. Intuitively, this term tells us that we should be able to discern the goal given the current state. We can effectively optimize this objective by training a goal condition policy to quickly reach a goal. Now, what about this first term? This term tells us that we need to maximize the goal distribution entropy. Intuitively, we need an agent that can set diverse goals that cover the entire state space. Most work on goal condition reinforcement learning assumes that there's a fixed goal distribution to sample from. But for an agent that autonomously explores, it must learn to set diverse goals for itself. At first glance, sampling goals from a high entropy distribution may seem easy. In fact, the maximum entropy distribution is the uniform distribution, so an equivalent objective is to say that we want to sample goals uniformly at random. In our two-dimensional example, it's pretty easy to sample from this distribution. But what if we have a more complex high-dimensional state space? For example, what if the state is an image? If we sample a random image, we'll just get meaningless noise. We instead want to sample uniformly from the set of natural images, or more generally, we want to sample uniformly from the manifold of valid states. The challenge is that we don't know this manifold ahead of time. This is where the method that we propose, called Skew-Fit, comes in. It's a method for learning to sample goals uniformly from the manifold of valid states, without knowing this manifold ahead of time. Let's first discuss how we can obtain a goal distribution to start with. Since we don't know the set of valid states ahead of time, we can roll out a stochastic policy to collect some states, train a generative model over the states, and then use this generative model to sample goal states for exploration. However, if our generative model fits the initial training data well, then the goals that we sample and the states that we see will simply copy the initial state distribution. I'll now present Skew-Fit, a simple modification of this procedure that can provably increase the entropy of the goal distribution. Before training our generative model, we first take the states that have low probability density under our initial state distribution, highlighted here in red. We then skew them so that they are given more weight, as shown in the bottom left. We then fit a generative model to the skewed distribution. As before, we use this model to sample goals, roll out our goal reaching policy, and repeat this procedure. Intuitively, if we give more weight to low density states, then this generative model will effectively spread out the probability mass to low density states and gradually increase the entropy of the distribution. More formally, how exactly should we weight the states if we want a uniform goal distribution? If we knew the likelihood, p of x, of each state exactly, then we could weight each state by 1 over its likelihood. After normalizing, we would get the uniform distribution exactly. In practice, we use an approximate likelihood, p hat of x, and also add in a hyperparameter alpha, which prevents numerical instabilities when p hat of x is close to 0. We prove in the paper that we don't need to approximate the density very accurately. Instead, as long as our approximate density is correlated with the true log likelihoods, then we can always increase the entropy of our goal distribution. We also prove that, under certain regularity conditions, this procedure converges to the uniform distribution over the set of valid states. In practice, this means that we can maximize the goal distribution entropy while still using expressive generative models, such as variational autoencoders, allowing us to scale to high-dimensional state spaces. Our overall goal is to optimize this equation. We presented Skew-Fit, a method for optimizing this first term. In our experiments, we combined Skew-Fit with a goal-reaching method for optimizing the second term, which in our case is reinforcement learning with imagined goals. We compared our method against prior goal-reaching methods, as well as a variety of exploration methods on a variety of simulated domains in a real-world door-opening robot task. All of these tasks are solved directly from vision and have no domain-specific reward or state information. The only input to the policy is the current image, and it must output the velocity of the robot end effector. During exploration, it's unlikely for random actions to result in interacting with the object, and so most of the initial exploration data will not involve moving the object. Thus, a method that naively trains a goal distribution on the exploration data will be heavily biased towards these states that do not involve interacting with the object. We see the policy trained with Skew-Fit accomplishing the simulated tasks. In the middle, we see a third-person view of the robot. In the top right, we see what the robot sees. And in the bottom right, we see the goal image. In this task, the robot must move its hand up and over the door handle and pull it to its correct location. In this task, the robot must pick up or push the ball to the correct location. In this task, the robot must push a puck to the correct location. Lastly, we tested Skew-Fit on a real-world door opening task, shown here on the left. On the right, you see an example image that the robot sees, where we can see both the door on the left and the black gripper on the right. After leaving the robot to autonomously learn for 5 hours, we then ask the robot to open the door to a specific angle by providing it a goal image. At the bottom, the first row shows a third-person view of the robot. The second row shows the state that the robot sees, and the last row shows the goal image that the robot is trying to achieve. As we can see, the robot successfully reaches a wide variety of angles. Without Skew-Fit, we found that the policy doesn't learn to open the door consistently. We can better understand why Skew-Fit performs better by examining samples from the goal distribution. If we look at the goals that the agent sets for itself when we don't use Skew-Fit, we see that the goals all have the door closed. In contrast, when we use Skew-Fit, we see that the policy sets much more diverse goals. Many of the goals involve interacting and open the door, which encourage the robot policy to practice reaching these different goals, rather than constantly practice to keep the door closed. In summary, we've provided a formal objective for autonomous learning. We've presented Skew-Fit, a method for tractably optimizing this objective. And we've demonstrated that it works on real-world robot tasks, directly from vision and without task-specific rewards. If you want to learn more about Skew-Fit, our paper, code, and website are available here.